Hello, all. Thanks for checking back again and again. Introducing chapter whatever, Thermodynamics. In our text, in the Zumba text, it is chapter 17. And this silly thing called free energy. No energy is free, it's going to cost you, but it's a way that chemists use to describe the total energy content in some system, collection of species of reactants or products. It's kind of a long story. I didn't know how to approach this extra supplemental video, so I just pulled out some old notes and I'm going to buzz through them. I wish I could ask. I wish I could ask if you have questions, but it seems weird talking to a machine. First law of thermodynamics, you know it already. Conservation of energy. You can't create energy, you can't destroy energy. The total energy in the universe is pretty much fixed, pretty much constant. Yeah, well, unless you take into account nuclear effects, but we're just going to say that you can't really create or destroy the total amount of energy in the universe. Although if you're tricky, you certainly can introduce into your system, whatever your system may be, you can introduce more energy by taking it from somewhere else. All right, the first law of thermodynamics again. Let's see, conservation of energy. But always in the real world, when you convert energy from one form to another, you end up losing some to the surroundings. So it gets away from you. Every time you convert energy from one kind to another, some is lost into the environment. This is way back long ago. I don't know if this is chapter 8 or something. No, it's not. It's before that. Chapter 6, perhaps, when we talked about changes in energy coming from heat flow and work done, pressure volume work. That's kind of a review, and I'm not going to worry about it too much right this minute. Important to remember that the change in energy or absolute energy, the change in energy is a state function, so it doesn't matter how we got there. All that matters is where we're at. Here's a good illustration. Most old-fashioned light bulbs with that little filament that goes around and heats up, and emphasis on the word heat, gives off a lot of heat. It's not very efficient. Of 100 watts that might be given to an old-fashioned light bulb like this, maybe only 5% of that, 5 watts, is converted into useful light, unless your purpose is to convert it into heat. But so that's what we mean. Usually we call the heat tax is the energy that's lost, usually to heating, every time we convert energy from one form to another. So if I burn a fuel like natural gas and convert it directly into heat for heating your home or something, that's pretty efficient. You don't lose much of the chemical energy available in the methane in the conversion. But on the other hand, if we burned a fossil fuel like coal to make boil water and make steam and then to turn a turbine to generate electricity, every time we convert from here to here to here to even transporting the electricity over the wires loses some heat. And then when you take that energy and run a device, you lose even more heat. So every time you convert energy, some is lost. Let's see. What does the word spontaneous mean? It means happens all of a sudden, all by itself. There's some push to make it go, but we may not have control or be able to directly observe what that push is. Chemical potential, before, free energy, after. Spontaneous. Well, for some reason, there are actually two forces in terms of thermodynamics that drive a reaction forward to make it go. One of them is the heat flow, but the other is this thing called organization or messiness. It's called entropy. Let's see if I can make this. Yeah, it's a little bit bigger. So in a physical sense, this weight had less energy down by the dude's feet, but now that it's way above his head, it has a whole bunch of gravitational potential energy. Same story for salt and water separate. If I have my NaCl on the bottom of the beaker and water somewhere else, that's an organized situation. But this is less organized. This is more messy. So what drives salt to dissolve in water? In one sense, it's the increase in the messiness of the system, and we have an official word for that as well. Which brings us to the idea that some processes are reversible and some are not. The reversible processes are the equilibrium processes, forwards and backwards. But is it possible to reverse the process of rusting from an old rusty beat up car in a field somewhere into a brand new, shiny, restored retromobile? I don't think so. So this is non-spontaneous backwards, but very spontaneous forwards. But whenever I do have an equilibrium, like we've been studying for the previous chapters, there's no change in free energy associated with that. Thinking back again, chapter 12, we talked about how fast a reaction goes, and that's the idea of getting from reactants to products to get up over that bump. This looks like an endothermic process anyway, but regardless, now we want to talk about the relation of the reactants to the products and what the likeliness is that this would make it over to this. Likeliness, is it likely? Is it not likely? Is diamond likely to refer back to graphite? Well, yeah, it is, but it's so slow that nobody wants to stick around to watch it happen. In a way, graphite is more messy, more disorganized, and diamond is more organized, more bonding and more order in the crystalline structure. So it could happen, but it's not going to happen too often. On an atom-by-atom basis, perhaps. Remember we talked about exothermic and endothermic. Endo means you got to go up the hill. That's pretty rare. Exo is very, very common. Most processes are exothermic. And there's a word for messiness or randomness or chaos, and it's called entropy. And we say that melting, for one thing, from a solid to a liquid creates more entropy. The difference between ice at 0 degrees and water at 0 degrees is the entropy. Water, liquid water, even though the same temperature, has more randomness, more entropy in the particles. And not only melting, but especially boiling. If I were to boil, so I said melting here, but boiling from a liquid to a gas increases entropy quite a bit. Factors affecting entropy and entropy change. Oh, yeah, here's enthalpy and here's entropy. They sound so similar. It's confusing. In the olden days, we talked about exo and endo. We know exo is much more common. But now we're introducing this idea of things like preferring actually to get more messy. They're spontaneous in the forward direction if they get somehow more entropy, more disorder. And there's actually a number that we can use to calculate that as well. So again, it's favorable for delta H to be exothermic, that is negative. It's unfavorable to be positive, but it can happen if the entropy increases greatly. So this dude, Boltzmann, came up with this equation that actually calculated with a constant and some description of the number of energetically equivalent ways to arrange the components of a system. So you can calculate it. It's actually based on the absolute zero temperature. A crystal has no entropy, but since we never really get to absolute zero, so it's temperature dependent. But here's another way to calculate. We'll look at an example of this toward the end of this if I get a second, if I get to it. So more favorable changes are more entropy. Delta S is positive. So if I end with more entropy than I begin with, so this term is greater than this term, then I'll have a larger number minus a smaller number, and I'll have a positive change in entropy. Oh yeah, all these things are really important in predicting if an entropy change will be positive. Going from a solid to a liquid, or especially a liquid to a gas, increases entropy. If you can create more moles of gaseous whatever, then you're increasing your entropy. Warmer temperatures have more entropy. More solids dissociating or dissolving into water, that's more entropy. Yeah, we've seen that already. Here's a calculation. These S numbers, these entropy numbers, are actually in the back of your book. Appendix 4, I believe it is. So we have 1 mole of Na sodium ions, aqueous, probably 1 molar as well. 59 joules is the measure of entropy. joules per mole Kelvin. Same for the chloride ion, same for this. I just looked these up in the back of the book. So here's the product. One product. Oops, products right here, and reactant. This is a physical change, isn't it? But still, what drives salt to dissolve in water is a positive entropy change. Not much enthalpy change, heat change. Here's an interesting one. Burning methane. I know all about burning methane. Do it all the time. So do you in the chemistry lab. But the entropy numbers, gaseous moles have much more entropy than solids and liquids, you know. I looked these up in the back of the book. They're in joules per mole Kelvin. So if I had 2 moles of water, 1 mole of carbon dioxide, 1 mole of methane, 2 moles of oxygen, I just fill them in according to that equation. You know what I'm looking at right there. Mm-hmm. So, yeah. But it all comes out to slightly negative. So it's hard to believe. This is 1, 2, 3 moles of gas. This side also has 1, 2, 3 moles of gas. So 3 moles of gas going to 3 moles of gas doesn't seem like much of an entropy change. But it looks like it's a little bit negative. But this is so close to zero, really, on the energy scale, that there's not much of a reason why this reaction wants to go forward in terms of entropy. But I certainly know that enthalpy, this gives off a lot of heat. So this is so exothermic that it really wants to happen anyways. Another way to say entropy change, going from a solid to a gas, has a huge entropy change. Look at all the randomness or more degrees of freedom that these particles of gas have than solids. Here's a graph showing the same thing. Not really probably a sketch, cartoon. Solids have a lot less entropy. Gases have a lot more entropy. Questions? Predict the sign, positive or negative. A hot beaker burning your fingers. Well, shoot, I don't know. You have to define your system. Maybe your system are your fingers. And so your fingers get more energy, so they get more entropy. Positive. Water vapor condensing from a gas to a liquid. That's not increasing entropy. That's decreasing to a liquid. That's from a gas to a liquid. That's negative. Separation of oil and vinegar in salad dressing. Well, it's a natural process, but if they get separated and more organized, that's a negative delta S as well. Dissolving sugar into tea, that's getting more messy whenever a solid dissolves into a liquid, aqueous phase. Let's see, here I'm generating 1 mole of oxygen gas from no gas, so this is going to be a positive entropy change. This side has 3 moles of gas, 4 moles of gas. This side has 2 moles of gas, so from 2 moles of gas to 4 moles of gas, that's increasing entropy. This will be positive. Aqueous phase ions have a lot of entropy, and solid crystals have a lot less entropy. So I'm gonna guess that one is a negative. This one's negative. I summarize those answers for you here. Let's see, how much time am I getting on to be? Oh my goodness, I don't have much more time left. I'll post more of these. You can look at them in your spare time. Do I have time to go through this one? Maybe I do. From a liquid to a solid, less entropy, negative. This is the backwards of the one we just saw. 4 moles of gas to 2 moles of gas, less entropy, so negative here, I'm going to say. Gas. 3 moles, 4 moles of gas created from 2 moles of gas. Let's say that's more entropy. More moles of gas, more entropy on this one. Solid, gas, solid. This has 2 moles of gas, and going to no moles of gas. So I'm focusing on the gas, you can tell, right? So this is a negative entropy change. All of the above. So what's the question? Which one have a positive entropy change? How about, what do we say, this one? Yeah, I think we said that one, right? No, not that one. We said this one, right? Gotta go, guys. Thanks for checking in. I'll see you in class.